Okay guys, this is the Unit 11 exam review video for May 2018 Algebra 2 Spring Exam. Dealing with some square root functions. So for the first set here, we're just kind of breaking down square roots. If we have a denominator that has a square root in it, we want to make sure that we rationalize that and get that radical out of the denominator. So for this first one, we'll leave 3 on the outside. But radical 24, we can break that up into two different square roots, one of them being a perfect square of 4. So we can do 4 times 6 will get us 24. And then radical 4 is 2. So we change that radical 4 to be a 2, and now on the outside we have multiplication. 3 times 2 is 6. So we get 6 radical 6. And that would be your final answer for that one. Can't break down radical 6. 19, we kind of have to remember that idea about a negative. When a negative's inside the radical, we have to pull out I. So we pull out I, and then we have our radical. If you know your perfect squares, you'll know that 144 is a perfect square. So if we take the square root of 144, we would get 12. Your final answer would be 12i. If it helps you, I will write the perfect squares up here. There's the first 10. We could do 121 and 121 and 144 as well. All right, 45. So we want to find, is there one of those numbers that goes into 45? We bring out our I because we have that negative. 9 does go into 45 5 times, so 9 times 5. 9 happens to be the perfect square of 3, so we can write 3 there. Typically when we write this, we write it as 3i radical 5. For 21, we want to find the perfect square that goes into 108. So let's see, if we do, this one might take a little bit of work, kind of thinking through which ones go into 108. We could do 16, 4, 16. Those look pretty good. I'm thinking maybe 36 and 3. And you can do these in your calculator. You can just, try it out and see which ones work. This section you are allowed to have a calculator on. 36 and 3 do work. You do 36 times 3. And then the square root of 36 is 6. So your final answer there would be 6 square root of 3. All right, now when we get to number 22 and 23, we have to rationalize those denominators. So how we rationalize is we multiply on the top and the bottom whatever radical we're trying to get out of the denominator. So since we have a radical 5 there, we're going to multiply the top and the bottom by radical 5. So we'll have 2 radical 5 over radical 25. So radical 5 times radical 5 is radical 25. Now, we kind of talked about a trick that you can write it this way. You can do the radical 25 and then break it down to 5. Or you can remember that when you take the square root of 5 times the square root of 5, or if you have the same number twice, then it's just going to be that regular number without the root at the very end. So let's go ahead and practice that on part B. So we're doing radical 3 times radical 3 on the top and the bottom. On the top we'll get radical 3, and then on the bottom we just have 3. You could put radical 9 there, but it's going to simplify to 3. So if you remember that quick trick, it'll save you a little bit of time. So when we get to something like 23a, we multiply by radical 10 over radical 10. Now on top we have 2 radicals, and when you have those, you can multiply those together and get radical 60, 6 times 10. And then on the bottom we will just have 10. Now 60, you want to see if you can break that down. See if there's a perfect square that will go into 60. And there is. 4 will go in 15 times. So 4 times 15, radical 4 times radical 15 over 10. Radical 4 breaks down to 2. And then 2 over 10 is the same thing as 1/5. So we'll have 1 radical 15 on top and 5 on the bottom. You don't have to write that 1 either. You can leave that 1 out. All right, now part B is very similar, except for now we have a constant or a coefficient and we have a radical there. So we're multiplied by radical 14 over radical 14. On the top we get 7, let's see, 50, radical 70, oops, over 14. And radical 70, one of the things about, is there a perfect square that goes into 70? There is not. What you would do to try that is you would just go in your calculator, 70 divided by 9, 70 divided by 4, you know, try them out until you know that there's not one that will work. But 7 over 14 will reduce to 1/2. So we can reduce that to 1 over 2. And again, you don't have to write that 1 on the top. All right, when we get to 24 and 25, this is solving and checking for extraneous solutions. So when we say solve, we mean for x, get x all by itself, okay, and then plug it back in to see if there are extraneous solutions. So first step, we want to get x by itself, we need to get that square root by itself. So we're going to subtract 7 from both sides. And then we will divide by 2. So on these, while you're solving for x, you have to make sure that square root is alone before you can kind of move further. Once the square root's alone, we square it and we square the other side so that we can cancel that square root out. So now we have x plus 5 equals 3 squared is 9. Subtract 5 from both the sides. And we have x equals 4. Now, we're not for sure that it's going to work, so we need to check and make sure that it'll work before we call it a solution here. So we'll plug it into the original, plug 4 in for x. We'll subtract 7. Oh, sorry. No, we won't. Plug it into your calculator. What am I doing? Or just do it in your head. So 2 radical 9 plus 7. Radical 9 is 3. And then, let's see, we would end up with 6 plus 7. And 6 plus 7 is 13. So we get 13 equals 13. And you are welcome to check those in your calculator as well. Make sure that those work. But the check does work, so x equals 4 is a regular old solution. Now when we get to something like 25, I'm going to go ahead and rewrite that. We can go ahead and square both sides because that square root is alone. So we can square both sides. So I'll have x squared equals 2x plus 15. And you can do this one of two ways. You can move the 2x and the 15 over, or you can move over the x squared. I'm just going to go ahead and move over my x squared, make life a little easier here. And now we have 3 terms, meaning you can do quadratic formula or you can do split the middle. I'm going to go ahead and do split the middle. I feel like we can always use more practice with this with split the middle. So we have -1 in front of that x squared. So -1 times 15 is -15, meaning that my factors of -15. So 5 and 3 would definitely work if we do 5 and -3. 5 minus 3 is 2, which is our middle. It's what we need. And then -3 times 5 would give us -15. So let's go ahead and split the middle terms. All right, and these first two, I'm going to go ahead and pull out, let's see, both these first terms, this term here, both have a negative, so we're okay staying negative. Let's go ahead and just pull out an x. So I'll have -x plus 5 there. And here I can pull out a +3. So I would have -x plus 5. So -x plus 5, since that's in my parentheses, that's one answer. X plus 3 is my second answer. I get that from these outside parts. So here, if we solve that, we get x equals 5. Oops. And then our x plus 3. Subtract that 3 over, we get x equals negative 3. Now we have to check both of those for extraneous solutions. So we'll have, let's go ahead and check 5. So we'll have 5 equals radical 2 times 5 plus 15. All right, so we would get 10 plus 15. Oh yeah, 5 equals radical 25. That one works. That is a regular solution. We're good to go on that one. Let's go ahead and check negative 3. All right, so we have negative 6 plus 15, which is radical 9. Radical 9 does not equal negative 3, so we would call this extraneous. So x equals 3 is, or x equals negative 3 is extraneous. So that's the section of the square roots unit that you can do with a calculator. Now we're going to get to the sections where you cannot use a calculator. And so the first one of those is the domain, solving for the domain. So for this one, we take the inside out. So we're going to go ahead and remove that 6x minus 5, and we're going to make it greater than or equal to 0. And then we just get x by itself. So we're going to add 5 to both sides. And then we're going to divide by 6. And we have x is greater than or equal to 5 over 6. Okay, and then if it says that you need to write it in set notation, that's where you do the x such that, and you put your curly brackets on there. That would be your final answer for that one. For 27, you would do the exact same thing. Take the inside out and put it greater than or equal to 0. And we'll get x alone, so we'll add 4 to both sides. Divide by negative 2. So we have x is greater, oops, I forgot our important thing here. We have to flip the sign when we divide by a negative. So now we'll have less than or equal to negative 2. And you can put your x such that. So remember to flip the sign when you divide or multiply by a negative number. All right, 28. Using the domain you found in question 26. Let's go back to 26. All right, so that is x is greater than or equal to 5 over 6. 5 over 6, if you were to put that in your calculator, you would figure out that's about 0.83 repeating. So we want x to be greater than or equal to 0.83 repeating. All right, so if we look at these 1 and 2, yeah, those are both bigger than 0.8. That one's 0.75, and 3/2 is 1.5. So C is not in the domain. C would not be in the domain for that one. All right, which equation below describes the function graphed on the grid to the right? So if we look at the regular square root function, I'm going to draw that one on here kind of roughly for us. We start at 0, 0. There's a point at 1, 1. And there's a point at 4, 2. And 9, 3. So this is kind of the general form, oops, I missed one. General form of the graph. Now, if we look at it, this one's been flipped over, our red graph here. It's been flipped to the left. That's a reflection over the y-axis. It's a reflection over the y-axis. That shows up when we put the negative on the inside with x. So if you look at your options, you can go ahead and cross out A and C. And then we know that it originally started at 0, 0. So if we go ahead and flip it, this is where it would be. And then it's also been shifted up 2 units. And that shows up by +2 on the very outside. So that would be D. Okay, our last question for the square root section. We need to write down our transformation. So first, the negative on the outside, that's a reflection over the x-axis. The -3 on the inside of our function, that means we shifted right 3. And the +2 on the very end is up 2. So our original is over here on the left. So if we want to reflect x, 0, 0 won't change. 1, 1 becomes 1, -1. So you basically just put a negative sign on the y values to reflect it over x. So kind of one thing that we used to say is reflect x, change y. If that helps you. Reflect x, change y on that one. Now we're going to shift everything right 3. So 0, 0, whoops, 0, 0 becomes 3, 0. We just shift every single one of those points 3 units to the right. And then finally, we're going to move everything up 2. So we're going from our previous graph. So I'm using the previous one, not the original now. So now my 3, 0 point's going to go up 2. 4, -1's going to go up 2. All right. And that is our final graph for that one. Now, when we talk domain, domain is your x values. So we're going to kind of talk about this 2 different ways. If you do it in interval notation, you would say that x is getting bigger, or is going from 3 to all positive numbers, to bigger positive numbers. So we could say 3 to infinity. We would include 3 because it's part of the graph. Now, okay, we really, really like it to write it in set notation when we talk about x, okay, and then we relate it to the number. So it's x equals 3 or greater than 3. So you could say x is bigger than or equal to 3, or x is greater than or equal to 3. Now for our range, even though our arrow is pointing to the right, technically our arrow is continually going down, 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 down to -infinity for our range y values. So we're going to go from -infinity, and it stops at a y value of 2. So you have to keep in mind, you're naming this one by y values. It goes from -infinity to 2. The way that we really, really like to write it is we like to say y is less than or equal to 2. So we're saying it can be 2, or it can be less than 2.